Okay, great. Okay, so today I would like to talk to you about some recent work we've been doing and try to convince you that there's something happening which is due to the continents themselves. The continents can do, I think, can go unstable and generate a lot of geological structures. They don't need anybody else. So common views that we've heard some talks about this, that continents are stable, but we know they're not that stable. They can get perturbed. We have rifts. We have sedimentary basins. They can get disrupted. China has lost the China Craton, which is old and which, by all means, should have been considered stable, has lost its continental root. And when we see that, then usually we seek causes in mantle convection, plumes, slab pool, or remote tectonic events. We always seek causes away from the continents. So are we stuck with this? Is this just the end? Do we just have plumes and slabs to work on? I would suggest there's something else. And so I will argue for top-down control for filled rifts, olacogens, swells, and intercratonic sedimentary basins. Why a top-down control? Well, because the lithosphere has been cooled from above. So, of course, there's negative buoyancy which is being stored. We all know that the contents are made of chemically depleted material which makes them buoyant. So we've got indeed two competing effects, and the question is whether one wins over the other. I would like to convince you in some cases, in fact many cases, the cooling will generate instabilities. The two things that will come out of that study is that even if we've got a reasonably thin layer that goes unstable at the base of the lithosphere because of the characteristics of that system and the high viscosity, you can generate large structures even though it's a thin layer that goes unstable. And the second thing is that because of the high viscosity, these are things that can last for a long time and can therefore escape the typical time constant that we have and that we associate with plate tectonics. So if you look, for example, at North America 500 million years ago, and I'll come back to that later in other areas, this was a time where we generated a lot of rifts. That's the southern Oklahoma olacogens. Then we have the real foot rift, which is prolonged in another kind of rifts. And there were lots of swells and basins forming at that time. We have the Michigan Basin, which started to form, the Williston Basin, which started to form, the Hudson Bay Basin that I'll mention later, and also some domes, the Nashville Dome, Cincinnati Arch, and other domes like that, all at the same time. And you can see also that there's another rift here. I forgot the name of it, Marathon something. One of the characteristics that they're perpendicular to the edge of the continent at that time, which is this dashed line. And you can therefore see if you try to explain all these rifts by the one and only mechanism, you've got a big stress problem because they've got very different orientations. The sedimentary basins were long-lived, so that's the four major basins that formed at about that time: Hudson Bay, Williston, Michigan, Illinois. And of course, some of them have been subsiding for a long time, suggesting that there's been a lot of perturbation to a very thick lithosphere. And the Williston Basin, in fact, is still subsiding, and it's been subsiding for almost 500 million years. Now, of course, these are old basins. We lack some of the information, and maybe the content has been changed since then. So it's also good to look at more recent events. This is a map of Africa with most of the activity that's there for the last 30 million years. I'd like to draw your attention, forget about this, because that's not something I think can be relevant to what I'm going to talk about. You can see this, all these volcanic centers that are scattered all around the continent. They're all active at the same time. You have, in fact, still basalts coming out near Libya over there. And the most interesting Cameroon line here. So all this is going on at the same time. This looks like a rift. In fact, the Cameroon line is about 1,000 kilometers, which is typically the length of these rifts, like these southern Oklahoma olacogens or the real foot rift. They're about 1,000 kilometer structures. The Cameroon line is very interesting because it's a 1,000 kilometer long thing. Activity has been sustained there for about 70 million years without interruption. So what you have is this piece of continent has been drifting with respect to the mantle, and yet there's been continuous upwelling and feeding of magma into the upper crust. That's a summary of all the ages that we have in this area as a function of latitude, roughly aligned with the structures here. You can see activity began about 70 million years ago and has been sustained throughout the length of the line. So throughout 1,000 kilometers, you've got 70 million years of volcanic activity. Bill?
Volume per time?
I don't have the data. In fact, I have the numbers somewhere. Basically, as I recall, my number is about, you've got 100 times less than basically an OY in a hotspot type thing. So it's very slow rate of upwelling, very slow rate of magma production. So you can see this is a very striking, no migration of ages and some activity which is exactly at the same spot for this very long length of time. So the main characteristics of these events, I think there's other examples in Australia, the Adelaide Basin and the Adelaide Rift, etc. There's a lot of examples elsewhere. So what all these structures say that these rifts do not go to completion. They stay there. There's no ocean basin forming. And these have been called failed rifts. And if you look at their deeper structure, there's absolutely no change of crustal thickness whatsoever. You have changed the crust because you've injected magma into it, but no crustal thickening, no crustal thinning, and certainly no crustal stretching. So if it's rifting, then it's rifting without crustal stretching. So summary of what I've just been describing, we have the most important thing is that all these events are synchronous. They happen at the same time. They can long for a very long time, so which means, I think, implies that these things are attached to the continent. They proceed over a long time scale at the same location, and they're organized in a very specific and distinctive spatial pattern. Linear rifts at the edges, network of swells and basins in the interior. So this is, I think, all these characteristics suggest that it's a process that is actually happening in the continent itself. The main features that I will, I think, explain with some of the work that we've been doing is that why is it so slow and long-lived? Why you have simultaneous events that are separated by very characteristic distances. And the one thing that I think is important is what this determines the length of a rift, and this is something we can explain with what I'm going to propose. And of course, the pattern itself will, I think, account for. So the lithosphere has been cooled from above. So what you have is that's the lithospheric mantle. It's made of depleted mantle that's been, out of which melt have been extracted. So it's buoyant, chemically buoyant, but it's been cooled from above. It's above the asthenosphere, which is also unstable. So you develop a kind of temperature like this. And I draw to your attention that you've got a temperature difference below the lithosphere, because we know that the lithosphere is heated from below. So we've got some convection going on and then some temperature difference. And this is an important component because that provides buoyancy to actually drive some of the instabilities of the material above. So you have two temperature differences that can drive the instability here. If you look at the parameters of the system, you can make the equation dimensionless. So this is a standard fluid mechanics stuff, not that important, but there's three relevant numbers here. One is the viscosity ratio between this upper viscous material that's been cooled from above and the asthenospheric mantle below. And it turns out that this number is irrelevant as long as it's larger than 1. It has a very small effect on the instability, simply because, in fact, what you're driving is the instability of a slightly more viscous material, and this thing here basically acts as almost as a free boundary. Then the Rayleigh number, which we calculate using the thickness of that upper layer, and with the total driving temperature difference here, mu is viscosity, kappa thermal diffusivity, rho density, g acceleration of gravity, alpha coefficient of thermal expansion. And then the new number here is the buoyancy ratio, which measures the ratio of the chemical temperature density difference, which is stabilizing here, and the temperature-driven density difference, which is destabilizing. And here, again, the total delta T is driving the instability, not simply the one across the... So if you look at the instabilities in the lab, I'm going to show you a few, and then we've done some theory for this. In a regime diagram forget about this viscosity ratio, which is irrelevant. You can plot a regime diagram in the Rayleigh number versus buoyancy ratio domain. And this was done through analytical work, numerical work, and laboratory experiments. And this is the boundary here between what's stable here and what's unstable. And there's two different kinds of instability. One here at high buoyancy ratio, where the buoyancy of the material is so large that it can only convect internally. It will not penetrate into the lower layer. If you will, the lithosphere will not penetrate into the mantle or the asthenospheric mantle below. And the most interesting one is the unstable regime here, which is oscillatory, which I will describe at low buoyancy numbers, in which the lithospheric mantle can protrude into the atmospheric mantle below. So you see, it's very robust. And the one very striking feature here, yes? Buoyancy ratio is if you compare your depleted mantle to the atmospheric mantle at the same temperature, same pressure, you've got the only the effect of composition, and that provides you with the intrinsic buoyancy of that material. Okay.
1% buoyancy between lithosphere and asthenosphere would convert to what?
The buoyancy ratio. Then, of course, you got to scale this to the temperature-driven density difference, which depends in a variable viscosity fluid and to the fluid that you can actually draw into the instability. So basically, you can draw about 400 degrees C temperature difference. So the thermal density difference is about 80 kilograms per meter cube, and the intrinsic buoyancy depends on your material. But if you look at xenoliths from various materials, it goes from about 20 to 50 kilograms per meter cube. So the buoyancy ratio is less than 1. You've got a stabilizing effect due to composition, which is not as large as the destabilizing effect of temperature. Does that answer your question? Here, yes. Yeah. No. Yes, but of course the temperature has a very small effect on density. So the chemical composition has also a small effect on density. So if you look at these effects, they're always these buoyancy ratios are going to be less than 1. You're scaling the effect of composition. I'll show you the numbers later. If you look at, say, typical Archean xenoliths, they would have a density difference with respect to the atmospheric mantle, which is about 40 or 50 kilograms per meter cube. And if you look at the thermal induced density difference, say, by 400 degrees C, you'll find about 80 kilograms per meter cube. So you scale 50 to 80, you get less than 1. Okay? So the one thing here is that if you talk about convection, you usually find that the critical Rayleigh number is 1,000 or something. Look at this number here. The number can go as small as less than 50. In fact, here you got nice theory for that. It's about 27. This means this thermal stratification is highly unstable. Why is it highly unstable? It's because you've got a very viscous layer that goes unstable against a very low viscosity fluid, and you've got the boundary to be able to deform. That's different from the Rayleigh-Benard convection, in which your layer is, in fact, in between two surfaces. Here, you've got all the lower surfaces to move up into. So very, very small critical Rayleigh number here. Very unstable system. So that's the low buoyancy ratio regime, which is interesting to us, because that's relevant for geology. A very small critical Rayleigh number, which means highly unstable situation. Large amounts of things can occur, as I will show you, and the large-scale structures can be generated much larger than the unstable layer itself. So just to show you things in the lab, low buoyancy ratio here, these experiments I will show you at about 0.25, I think. So what you have is the buoyant layer, viscous, and we're going to start cooling from above. So it starts protruding. You see these fingers going into the fluid. Now the interesting thing is that it's oscillatory, because what's driving the instability is the thermal effect, and of course temperature equilibrates rapidly, whereas composition does not diffuse away rapidly. So these fingers, as they protrude, they equilibrate thermally. They've lost their driving density difference because of the temperature has gone. So what's left is their chemical composition, which makes them buoyant, and they will pop back up again. And this is the next stage. You see it comes back up again. And then you can go into another cycle of instabilities. So it's oscillatory in character. If you scale this with typical values that we can estimate for lithospheric viscosities, the time scale for these things can go from about 100 million years to about 1 billion years. Unfortunately, we've got some slack because of what is the relevant viscosity for the lithospheric mantle. But you can see these are long-lived, long time scales for the instability. Michael?
In this limit, do your fingers that protrude down and come
Yeah.
back up
Yes.
always move synchronously together? Or do they sometimes start moving up and down randomly with respect to each other?
So the question is, do these fingers show up always at the same time? or is it random? No, the initial instability is synchronous. The thing goes unstable. In fact, that's the first one. And as the successive instability cycles continue, then they start to become not synchronized. So what you have is randomness appearing in the system. But the initial instability, as you can see here, is very, very much. That's the first one. Then it becomes much more chaotic. Now, of course, continents are a finite size. And if you want to look at spatial patterns, we have to look at 3D. So what I'm going to show you now experiments that were done in a continent of finite size. Now, unfortunately, we just could not generate continents with the shape that we see on Earth. So we've just started with a simple, circular continent. Sorry about this, but we can talk about the shape if you want in a discussion. So this is the layer that we're going to make unstable. And this is what you see. That's a thin layer, and you can see that you start generating these spokes, these radial spokes. And in the center, it's not visible here, but I'll show you pictures that show it. Then we have a more polygonal network in the interior. You see these very characteristic spokes on the outside. If you want to look at nice images, that's one thing from a sloping angle. You can see the fingers or the things that go unstable. And that's a planar cross-section across the fluid. That's a laser light that shines through the system. That's only lighting a plane, so you have a planar cross-section. You can clearly see the same kind of features that we... Yes?
So it's contact. Do you actually have the buoyancy that's spread out on the...
Well, no, we work it out so that the spreading is basically negligible. By the time these things go, the temperature effect counteracts the density effect, so they stop spreading. There's no measurable spreading over the course of an experiment. Now, if the layer is slightly thicker, then you can see, of course, the spokes are far in between, and you can start to see the polygonal network in a better way. So the pattern that you generate is this one. In an outer region, we've got radial spokes. That's the only way you can generate the instability, because the only way the instability it has to get fluid around and gather it. So you can't gather it parallel to the boundary. You've got to do it this way. And then the polygonal network at the interior. So you can see we have several things we can measure: the spacing between the spokes, the lengths of the region that's affected by spokes, and the spacing between the polygons in the interior. And everything scales right. I'm showing you experiments for b equals 0.3, which I think is relevant to some lithospheric cases. So wavelength scaled with the radius of the continents as a function of the aspect ratio of the continents, thickness over radius. You can see, of course, that's a proportional relationship here. So R goes out. And so basically what you see here is that the distance between spokes scales with the thickness of the layer. And if you look at it, the numbers, the wavelength is 5.3 times h. Here. If you want to look at the distance between hexagons, then they're separated by square root of 3 times this lambda, so it's 9 times h. So that is to say that even a thin layer will generate structures that are spaced by about 10 times the thickness of that layer. So think about a 50-kilometer thick layer at the base of the lithosphere. It generates structures that are separated by 500 kilometers, basically. So a thin layer can generate geologically relevant distances. The length of spokes in the outer region, S over R, we scale these again by the radius as a function of the aspect ratio, thickness over radius. Now, this is a very simple argument that I don't have time to go into, but you can see that when the thing goes very thin, then you've got much longer spokes. So we've got all these scalings. So I think for geology, what we can interpret is that the outer region radial spokes, what you have is linear upwellings, linear downwellings. So you can generate rifts perpendicular to a continental margin. In the interior, you got a polygonal networks, which will form a network of basins and swells associated with thinning and thickening of lithosphere, not crust. If you add phase change, of course, upwellings can induce decompression melting. This is a series of numerical experiments done by my students. And the green parts are, if you add some phase constraint, then you can generate, of course, melting in the upwellings if you got the right conditions. So you can see, I think we've got here some possibilities. Now, whether this really occur in nature requires the scaling properly. I think one of the best tests of this is, can we account for when it occurs and when it does not occur? And so for this, then we consider the density differences. So we know that on average, the composition of the subcontinental lithospheric mantle varies with age. It's depleted and varies as a function of age, so that's very old stuff, not so old stuff, and stuff today. And basically, say this is about the lithospheric mantle of today. The density on average at standard room temperature and pressure, 337. Proterozoic material, this is an average from a lot of Xenolith studies by Griffin and O'Reilly, 334, and then Archean, 331. And you can see, therefore, that the chemical density difference is about 20 to 30 for Proterozoic lithosphere, or 40 to 60 for, so that's the sensitivity between that stuff and that stuff, which is probably the lithospheric mantle of today. So you can see it varies. If you scale this, this is a buoyancy number which is in the regime that I've described. This probably puts the lithosphere into a regime where it doesn't go unstable in the same way, and you need much larger driving forces to make it unstable. So you would expect most activity to occur on Proterozoic lithosphere.
Mitigated by having higher temperatures, because then you have a greater delta T.
Well, you're talking about, say, in the Archean. I'm talking about today, because I'm looking at it today, and that's indeed an interesting question, whether in the Archean these things could go unstable. I think there's an argument for that. Yeah. So let's look at the evidence. So that's Africa. You can see that all this activity is there. That's the more recent lithospheric mantle. The Archean cores are there. There are dashed lines. And you can see that these structures clearly avoid these Archean blocks. They're away from these things. If you look at the intracratonic basins of North America, these four ones, well, there's a lot of Archean cratons in this area, but again, these basins clearly avoid the Archean cratons. That's a tectonic summary of North America. Here we're in the stable platform, the super province here, the Urn, the Slave, they're all Archean, with Archean keels. And here you got the Trans-Hudson belt, which is Proterozoic in age. And you can see that Williston and Hudson Bay have got all their cores exactly in that Proterozoic area. So you can clearly see these instabilities clearly avoid the Archean parts where presumably the lithospheric mantle is too depleted to become unstable. So the summary of this is, I think we've got to allow for these kind of instabilities because the Rayleigh number is so small that it's very unlikely that you can stabilize systems like this with such small Rayleigh numbers. Basically, it's with nature going on as the way it is, you'd have to have a very homogeneous and very high buoyancy material to be able to offset these kind of instabilities. In terms of what these instabilities can do, instability of a thin basal layer, even though it's very thin, can generate very large structures. You always think in geology that things are about as wide as they are deep. Here it's clearly not the case. What I've shown you is that this instability generates large structures. So something thin will produce things that are separated by large distances. We can also explain the length of rifts. If you scale this again with 50 kilometers, given the south constants, we produce basically these radial spokes that I've been mentioning are about 1,000 kilometers long, exactly like they're observed. Instability is slow, and it develops in several hundred million years. That depends on lithospheric viscosity, which is something that needs work on. But again, these are slow, and these are things that are completely separate from the Wilson cycle. They're not completely independent of it, because, of course, these instabilities develop at the edge of a continent. So when you create a new edge, you will generate a new instability. But then they will develop very slowly. The depletion of our Archean lithospheric mantle is probably too strong to low instability, and I think we've seen evidence for that. And the younger continental lithospheres are quite likely to become unstable. The predicted results are we should have continental-wide activity spread out over the whole continent, simultaneous, and with a very specific spatial pattern, rifts at the edges, and a series of swells in a polygonal network in the interior. The important governing properties for this type of mechanism is, of course, the degree of melt depletion with implications for density and viscosity. And of course, there's nice tricks in nature. You can start with depleted material because it's old, but then you can rejuvenate it. And so maybe there's there's a scope for rejuvenating arcane lithosphere, say by infiltrating melts or infiltrating metasomatic fluids, etc. But that's the important thing that we've got to watch for. And then we have to account for the fact that continents are basically a mosaic of different bits and pieces, and that the geometry is complicated. So we've done experiments with other kinds of geometries. Of course, they will affect the results, and that's, of course, something that you will have to worry about if you want to work in specific areas. Yes?
So when you started, you said that the viscosity ratio wasn't important. But here you say that the lithosphere mantle is too strong to allow its stability. And down here you say you need to track the role of diffusion on viscosity.
Yes.
None of those three things are
Because it comes into a Rayleigh number. If you've got, say, something which is completely rigid, so the viscosity of 10 to the 30 pascals, that's it, you're dead.
It's the Rayleigh number of the lithosphere.
Of the lithosphere, of course, of the lithosphere, yes. Okay, and so if
So you're saying the viscosity ratio doesn't matter.
doesn't matter, but of course,
As long as the
yeah,
lithosphere can flow,
yeah,
it will fall off.
exactly, yeah,
But it's really the viscosity
Yeah.
or the
Yep.
lithosphere.
yeah. When I explained the Rayleigh number, I said this was the Rayleigh number was calculated for the lithosphere, not for the other, because that's the one that goes unstable. Yeah, yeah. Bruce.
The time span we have for the instability, is that the initial formation or is that the duration of this development?
That's the oscillation timescale. That's the yeah.
So what would be the time scale for how long could these things oscillate for?
Well, eventually, depending on the strength of it, then you can undergo mixing. So if you got a very large Rayleigh number, then these things will mix. You will lose your roots and the flow. What happens is that some entrainment, as these fingers protrude downwards, then they curl, and then as they go back up again, they entrain some material. And so what you have is a mechanism actually to grow lithosphere. And then eventually, if you're too strong, then your fingers protrude, and then they get lost. They get mixed. Roberta?
I was just reading Barbara's paper that she published in 2010 on North America looking at seismic anisotropy, and they had a very nice argument for delineating the base of the lithosphere across North America based upon changes in seismic anisotropy.
Yes.
That base of the lithosphere, it turns out, is a little bit thicker in the trans-Hudson origin than it is out in the Archean regions adjacent to it, which is kind of sounds the opposite of what you're suggesting here. So are these two observations or her observations at, contrary to what you're preaching?
No, because I think the Trans-Hudson, the instability has, in fact, it might actually work better because the instability has done its work in the Trans-Hudson. We've generated the basins. Now the basins have been recording subsidence, so now we've got the material that had come back up again. As I said, there's a bit of mixing, so in fact what you might end up with is slightly thicker lithosphere than before when these fingers go back up again. So what you have now is not the mantle that went unstable and then thinned. It's the mantle that got back to its original status before. Because subsidence has still been going on uninterrupted in the Williston Basin, so you just can't have something going down right now.
Somewhat following up Bruce's question for a moment, I was wondering if you had a sense of what imposed shear would do to the instability.
Of course, shear will do lots of things. If you have lots of shearing, depending on the speed, etc., you can shear it off.
Well,
So.
a simpler question, do you have a sense of how it would shift the regime diagram and stabilize potentially?
It will act as a stabilizing agent, yeah, because it will shear things off, but it will also align some of the structures of the mantle flow. So, yes?
I wonder if you thought about the mid-continent rift and whether it should be displayed by some.
Yes, of course, I thought about it. And the mid-continental rift has several nice characteristics. It has a branching pattern, which is reminiscent of what we observe. It branches out to the Nipigon embayment to the north as it curls along the superior basin. Most interestingly, it's linked to the Granville orogeny, which is a bit of a bizarre orogeny, which is not that well understood. So what you have is extension beneath the mid-continental rift and compression in the Granville area. So this is a kind of alternating patterns of stresses which can be produced by this kind of instability. The mid-continental rift has, at least in the Nipigon embayments, there's been activity recorded depending on the span of the ages. If you take the errors, etc., it's up to 100 million years of activity for melting or magmatic activity in mid-continental rift. between the earliest signs of activity and the latest ones. So very long, prolonged, long-lived magmatic activity in the same place.
But the main period of magmatism was very short, right?
Sorry?
I thought the main period of magmatism was very short.
Well, it's of course there's a big burst of activity initially, and then it's there's still in fact as the ages pile up again. In fact, that vision may be oversimplified. There's more and more dates showing that it's actually lasted much longer than what was thought before.
It wasn't clear to me what started all this. What starts an episode?
Well, I think if you modify your continent boundaries, say you split your continent, then you create the new boundaries, and then I think there will be, indeed, these basins, this rift usually are happening not so long after a big continental breakup. That's only the case for these North American ones.
So you should see this cycle repeated after each supercontinent.
Well, then I think it's interesting is that these things are, the Wilson cycle is operating on its own time scale, and this thing is operating on its own time scale also. So you might have quite a complicated series of possibilities there. If they're in sync, then you're fine. If they're not in sync, if you start splitting your continent apart, you will generate new structures. But then depending on whether this continent will be drifting around before hitting the next continent, it may go unstable several times over. And that depends, of course, on Now, the average collision time, if you look in the past, it doesn't vary that much. It's about, on average, it's collisions between continents, formation of supercontinents, about 500 million years. So they're not that far apart, these two time scales. Greg?
Now that I understand the viscosity ratios, one thing that's interesting for Alan McCurdy's question is that if that ratio is under 1, then you would be shearing the base of the lithosphere, which would decrease its viscosity, which would have a promoting effect rather than
Yeah.
a lifting effect. So one kind of interesting thing to propose is a continent that's stationary and whatever reference frame you care about going to behave differently than one that's drifting.
Yeah, of course, yeah. No, the effect of the viscosity ratio, that's done on a series of calculations, standard stability calculations. It's a minute effect on the Ray number. You can understand this because certainly the lower boundary of the system can deform a lot. So as long as the lower layer is not very much more viscous, which would prevent this boundary to deform, then this is what matters. Yes, you had it.
Yeah, I was wondering if you get the same ratio between the lithospheric layer and the structure in this basin, for example, in both the numerical and the laboratory experiment.
Sorry?
If you get the same ratio between the lithospheric layer and the length scale of the structure,
Yes.
both numerical and laboratory experiments.
Well, the laboratory experiments are scaled, so of course they're much smaller, but I'm not sure you're talking about the widths, and we varied. The aspect ratio we varied. So when I'm showing plots like this, we've got continents of various thicknesses, various radii. We did about 70 experiments with all kinds of aspect ratios. So that's why we can scale things independently.
In your numerical model, the lithosphere has a viscous behavior.
Yes, it's Newtonian viscosity, yeah. And these calculations were done with temperature-dependent Newtonian viscosity, but not... now, sheet jasting has done calculations with non-Newtonian material, but you can talk about that, I think. Yeah. Michael?
For many of the applications, the amplitude of these oscillations surely must matter.
Yes?
How does the amplitude of the oscillation scale with V and the Rayleigh number?
It increases with the Ray number, in fact, with the ratio of supercritical Ray number to critical Ray number. And we haven't got the theory for that, but we've got the data. So the larger the Ray number, the larger the yeah. Yes.
So what's the observable gas today beneath North America? I mean, as US Ray gets further east, we can actually see much more detail how thick. I mean, potentially see features beneath these basins that you're talking about.
That would be lovely. If you look at crustal structure, there's nothing there. I've tried. So North America is, which I think is expected, because of course, if you talk about the effect of temperature-dependent viscosity, the upper part of the lithosphere is too cold to deform. So what you have is something which is stuck to the, say, temperatures are above 1,000 degrees C or something like that, where the material is able to deform significantly. So the lithosphere acts as a nice buffer so this is why the crust is not stretched or thinned. But however, because of the thinning, if you have looked at simple phase diagrams, you would produce melting by these upwellings, and so you would inject a lot of melt into the system. So I think whether you could still see traces of those melts in the lithospheric mantle, I don't know. And indeed, the major structures that we should observe would be in the lower lithosphere. That's where you should look for.
And what would we expect to see?
As of now, in these basins, in fact, I think we've done some calculations for the substance of these basins. Now, basically, substance is gone. So I think you've returned basically to normal. There's not much to see. I think the nice thing that you should go for is to go to Africa, because this is where the stuff is happening right now. There's lots of things happening in Africa. And there's nice work by Andy Nyblade and also Mike Kendall and Ian Bastow in Cameroon. So there's some lots of seismic stations there. There's data, and there's something where there's clearly an anomaly in the mantle, in the upper mantle beneath Cameroon, which is confined to the upper 300 kilometers. It's not down below, so there's no mantle plume, nothing. It's clearly something which is shallow, and maybe we can delineate this a little bit more carefully. But there's no crustal thinning, but some mantle anomaly which is confined to the upper part of the mantle. Kent? And
These drips, I'm still not clear. In your model, the drips came down and they all went back up.
Yes.
What's the analogy of that in the real world?
Well, if you, of course, that's when you would think, if you look at some continents which have lost, you've got Archean roots, and you, for example, North Sun has lost its root now, and there's maybe some cases to be made elsewhere. So if you start losing the root of one continent over 3 billion years, you should have lost, statistically we should have lost all roots. How is it that we still have Archean things and Proterozoic things? I think it's because, indeed, they come back up again. More than that, I think it's even one mechanism by which we can thicken the lithosphere. So I think to look at whether this makes sense or not, the one thing that I'm sure of is that to produce this kind of synchronous activity, you need something which is attached to the continent. You just can't generate it by having plumes wandering about and southern plumes or whatever. So clearly, I think it's something which has to do with the continent. The second thing is that I'm sure that the instability can only occur in the lower part because that's where the viscosity is not too high to prevent any motion. So this is where we should look for the evidence. Now, whether we can detect this or not is an issue, but if we had lost all these lower parts of the lithosphere and then never recovered it, then we should have statistically, we should have mostly thin continents because they should have all gone unstable and lost their roots, which is not the case. So I think this is one mechanism by which they do not lose their roots. They go unstable, but they keep their roots, in fact. Chiche?
I guess we actually have a poster tomorrow on the numeric model of almost exactly the same kind of process. And the results for the Newtonian rheology, I mean, we really agree with the laboratory results, but we also look at non-Newtonian rheology, and we kind of try to apply that idea to the North China craton structure. So that's just one pricing. I guess it's always this the denomination that I said, historical instability. It's always kind of struck me that you look at some of the observations from the seismic, you can sort of see that really sometimes the denominations start right immediately from the bottom. And it's like the entire lithosphere actually going down. I mean, I guess even in a recent work by Greg Hossman's group, and they look at the Tectonic basin, I guess somewhere in East Europe.
Yep.
And they actually even seen this inhabited lithosphere that kind of seismicity into. So it's really, really cold stuff that got into somehow, wind unstable. So it's kind of curious, if you think with standard rheology that Greg we learned from laboratory studies, that those are really cold stuff. Somehow they go unstable.
Well, there's several things. First, we also did the theory, so it's not only the experiments, but indeed, there's two things. One is that the coldest part of the lithosphere is, of course, higher up, the one that's just against the astrosphere is at the same temperature. So it has to be coming from the coldest part. So how up you can go. Now, also, these experiments are working out of necessity. We just generated one fluid with one chemical composition. So we know that the lithospheric mantle is not sometimes built in one piece. There's several layers. So you might have, in fact, some internal stratification, which may in fact, play a role. And in fact, we know from evidence in several, say, the South African craton or the Superior craton, they're not exactly the same stratigraphy. They were probably not built exactly the same way. But that's still, so you might have a stratification which is not as simple as the one we've looked at in the lab. Doug?
Yeah, I was wondering if you had thoughts on what, in order to test these models, we could make observations with anisotropy, or something like that. For example, in the Cameroon case, I was involved in that experiment with anti-nitrate, and we found a very different pattern of anisotropy along the Cameroon volcanic line, where where you had that strong mantle signature.
Yeah, we did look at a lot of data, but the paper is just out, so we haven't looked at all the data. I know you've done that work on anisotropy, and I must pay attention to it. I've had it somewhere, but we didn't look at all the data. The one things I wanted to look for any evidence for crustal thinning, things like this, because it would not sit well with this kind of model, and no evidence across the southern Oklahoma Lackagen, nor along the Illinois Basin, nothing. Cameroon, there's no crustal variation to be seen. And so this was the major thing that I looked for.
You would want to get large enough strains to sort of accumulate something.
Yeah.
What sort of strains you're getting sort of order 3, 4?
Sorry?
What would be sort of the order of magnitude of the strains of these observations? Do you get sort of
The strain, you mean?
Yeah. You get sort of 3, 4, 10?
No, we had 3, 4, yeah. No, not much more than that, yeah. We've calculated the forces it's easy enough to calculate the force. It's smaller than we've talked about rich push. It's a bit smaller than rich push, but not by much. So it's still not that far from all these other plate tectonics forces. The main thing, I think, is that we all know that if we look at the forces that are available and we know the strength profiles that are calculated, we've got a big problem. That if we look at all these forces, we just can't generate all the geological structures because our materials are too strong. So we need to do something about it. And the only way out, I think, is to have melts lying about and infiltrating. I think, Greg, you've worked on this. But so we have the same problem. If we're just looking at this material as strong as it is, then with the forces that I've got available and the forces that are driving this system here, we don't have the forces to make this thing stretch as it is. We need the melts, I think.
Okay, one last question.
I've got one last slide. Sorry. Yes? Well, no, you shouldn't expect more. You will have generate substance. Well, we wrote this paper with my students about subsidence of these basins. Basically, what you're replacing is the net effect in terms of density is not that large. You're replacing material that was chemically buoyant and that was colder, and then it went back. Then you've entrained some of material which was from below, which was hotter but chemically denser. So the net effect is not that large. So I would not expect a lot of topography. If you do numerical calculations, you generate some topography, but mild. It's not big. However, you will generate a big cooling effect, so you might generate quite a bit of subsidence, not a lot of swelling initially when this thing goes back up. Yes, just to show you, you should not always look for the culprit or the guilty party very far away. It might just be right there. So that's it. That's it.